Hi all, welcome to Stat 218. We're moving today into chapter 8, and it is all about paired data analyses. So first off, there's that cartoon, that's a joke. If you don't get it immediately, you should pause until you laugh, and then you move forward. Okay, so to put things in perspective, we finished up chapters, 1, 2, 3, 4, 5, 6, 7. 7 was all about comparing two quantitative means. The response variable was quantitative, and the categorical explanatory variable had two different levels of it. We're going to see in this sort of table throughout the rest of the term, all of our methods pigeonhole nicely into whether the response variable is categorical or quantitative, and when the explanatory variable, is it categorical with two or more levels, or is the explanatory variable quantitative in nature? And we're not really covering logistic regression, but to put things in perspective, chapter 7, 8, 9, 10, 11, and 12 is where we're going to finish up. So today, we've got data that comes in natural pairs, paired data analyses, if you will. So in many situations, you take paired data from two populations, okay, and compare the population means. Now, let's think it through. How would you take pairs of individuals from separate populations? I'm remembering back to when I was in high school, there was this thing called the Kaplan class to help you prepare for the SAT. And presumably they claimed that you increase your SAT scores by about 30 to 40 points by taking their class. And they did that by doing a before and after study. They had everyone take the SAT before the class, and then they had everyone take the SAT yet again, and they found the gain in the number of points. Okay, then took an average, and from that they developed a confidence interval or tested a hypothesis about whether the average was zero or not. Similarly, if I was comparing back years ago, my local grocery store options, Vons and Ralph's. In SLO, you still have that option, but in Los Osos, where I live, it's Ralph's and Grocery Outlet now. But if I was in San Luis, I could go to Vons or to Ralph's, and I would think the best way to compare the two grocery stores would be to go and literally, on the items that I buy, get the price on those commonly purchased items at both stores. So the two separate populations are the two stores, but the items that I select in common between the two stores form natural pairs. Similarly, if you're going to maybe try to find out I don't know, let's just talk about that example later on. Okay, in paired data, let's start with a quick example. In a psych class, they asked the students to memorize 20 nonsense words, and they told the students, hey, at the end of the class session 1 hour later, you're going to be asked to repeat these words back in and write down what they are. One of the words, if I remember correctly, was Zurfblatt, Zurfblatt. Clearly nonsense, it doesn't mean anything. But some of the students did pretty well. One of the students remembered 18 of the 20 words, one only 16. Shoot, one only 7. The students were not told that at the beginning of class, the next class day, they learned the words on a Tuesday. On Wednesday at the beginning of class, they were given the exact same test, and they were asked to repeat those words that they had memorized. And the scores looked like they were a little bit lower. One of the high score was 14 other words. The low score was 4 out of those words correctly. So I want to know, is there a difference between 1 hour later and 24 hours later? In other words, do people maybe forget overnight some of those words? So I'm thinking that's hard to tell, and I'll tell you right up front, if I calculated the two separate sample means, two separate sample standard deviations, and did a regular t-test as though they were independent, and not taking into account the fact that some people are just good at memorizing words and other people are not good at memorizing nonsense words, I wouldn't be able to tell the difference. But if I told you these data come in natural pairs, you see that in the case of every single student, from 1 hour in the bottom at the end of class one day to 24 hours later, the beginning of class the next day, every single student forgot at least some of the words. The most dramatic forgetting was the student who had 11 words correct and dropped down to 4. They forgot 7 words overnight. So I might want to know, like, a confidence interval on average, how many words of 20 had been forgotten overnight, or perhaps like with a hypothesis test, did people tend to forget on average overnight? Okay, so really what we've got going here is 2 separate columns of data, if you will, and in one of those columns, I'll label it Y1. Okay, in another column, it's labeled Y2. It's the before and the after score, if you will. Before minus after, okay, or perhaps after minus before if you want to go the other way. But in every case, there's a difference. It's the one value minus the other. We can summarize those differences by the number of differences, N, the average of the differences, d bar, and the standard deviation of the differences, s of the differences. Okay, and ideally, if you're thinking about a hypothesis test, if the average of the differences equaled 0, people didn't forget words overnight. The mean number of words the next morning equals the mean number of words at the end of class the day beforehand. A confidence interval for the difference, mu sub d, or if you will, mu1 minus mu2, is the average of the differences plus or minus about 2 standard errors, where the standard error is s over root of n. That looks just like chapter 6, the confidence interval for one mean. Literally, the confidence interval for one mean of differences is the method we're going to be using. Okay. So I'm not going to sort of go ahead and do these data with by hand or with Minitab. I'm going to be going ahead to give you a couple different examples, but maybe let's start by showing you how you could get those differences, the standard deviation of the differences, and then the number of differences in the context of a data set that we've looked at in a recent quiz. These are data on some public universities, 20 of them: East Carolina University, CUNY Queens, Southern Connecticut State, Montana State, UNCW, etc., across the whole group of those schools. There's 20 of them. There's the in-state tuition and the out-of-state tuition. Each school has one of each. So it's like the 2 separate populations are the in and the out-of-state tuitions. And each individual school has, again, an in-state and an out-of-state number. These are public schools, and so they're going to have one of each. Now, some schools, there's not much of a difference between them. In some schools, there's a huge difference between them. In any case, I want to know, how big is that difference? Literally, I guess what I could do is to calculate a new column. This is not what you're going to have to do again. I'm just walking you through the logic of this, and we're not doing the calculating bits, but the difference or the increase in the in-state tuition versus out-of-state tuition versus in-state tuition. I'm going to say that that formula is the out-of-state minus the in-state tuition. This new column called the increase is how much higher the out-of-state is than the in-state tuition. So for example, 7248 minus 764 is 6484. Okay. So for these increases, I want to know about the means and the standard deviations and all that good stuff. First off, you should know there's 20 of them. That was easy. But under analyze, the distribution of the increases, the key bits of information you're going to need to know to tackle this problem would be y bar, or d bar, I should say, d bar, then the standard deviation of the differences and the number of differences, and perhaps even the standard error for the differences would be helpful. So let me see if I could circle those. There's 20 data points in total, averaging 4180. and the standard deviation is 1364, but heck, as long as we have the standard error, S over root of n, we're going to go ahead and use that. Okay, so let's go with those bits of information. Ah, man. No, I'm going to put that back. I'm going to call that d bar, and sub d, the number of differences, and then the standard error for d bar. Okay, that's 4180, 305, and 20. Okay, now we can go ahead and implement the method. The method again here is the average of the differences plus or minus 2 standard errors. Now that actually shouldn't be plus or minus 2, it's plus or minus a t-value, which is based on the degrees of freedom. In this case, our degrees of freedom is 19. I could find that real quick. Where is degrees of freedom 19? I'm gonna look over here, find 19 degrees of freedom. And from that 19 degrees of freedom, on my t-table and the proper column, you can see 19 degrees of freedom down towards the bottom. Let me maybe pick a different color to highlight things. And so for 19 degrees of freedom, we have 95% confidence, 2.093. That's t, the t-value that we need for 95 degrees of freedom. Okay, so let's go with the big old blank. Okay, shoot. I forgot to write that down. 2.093. Now, we're ready to go. So d bar plus or minus t times the standard error for d bar is going to be 4180 plus or minus 2.093 times then 305. 4180 plus or minus 2.093 times 305, and here's where I should hunt for my calculator. So to do that, I'm going to pause the recording for a moment, and I'd encourage you to pause your recording as well. So I now have, just to verify that you could get the following calculation, 638, or if you will, if you want to write it in terms of a lower and an upper end, 4180 minus 638 is going to be 35. Oh, shoot, 42. If I did that right, up to 4180 plus 638, 49, 40, 48, 48, 18. You should check both of those numbers to make sure I got them correct. If I didn't get them correct, my mistake, report on that somewhere in the chat or the discussion forum and remind everyone of where you found the correct answer and how wrong I got it. Okay, so how would I phrase my answer? I am 95% sure, or we are 95% sure that the out-of-state tuition is 4180 plus or minus 638 more than in-state tuition in the year that we collected the data. On average, again, our sample size 20 allows us to conclude something about the greater population of all public schools nationwide, because we have a random sample of all public schools nationwide from which to calculate our numbers. So pretty straightforward, pretty easy to go with. Okay, so getting back into the rest of the lecture, testing a hypothesis. If I was trying to test a hypothesis, my null hypothesis would be that there is no difference between before and after, if you will. Mu sub d is 0, or maybe in the context of the colleges, that there is no, excuse me, that there is no difference in the tuitions on average between in and out of state. On the other hand, we've got three different types of alternative hypotheses. There is no difference, the difference is negative, or the difference is positive on average. My test statistic looks like you'd expect it to. It's a comparison of what you did see in the data to what you expected to see if the null were true, divided through by a standard error of your estimate of the mean of the differences, mu sub d. D bar is an estimate of mu sub d, and again, n minus 1, p-value and conclusions just like before. Not a surprise at all. So let's look at our data and see if we have the information there lying around. Oh, our confidence interval for the mean, 4118 to 3541. That's exactly what we got before. We're happy about that. But again, let's write down d bar equals 4180. S sub d is, well, actually, let's go with the standard error. SE, d bar is 305, and n is 20. So my test statistic t, oh man, I should not have erased those. So 4180, 305 is the standard error, and n is 20. Okay, now let's go ahead and calculate our test statistic using this approach here. We've got d bar 4180 minus what it should be on average if the null is true over the standard error 305, and that is a ratio of, well, that's hard to do. Let's do the calculator. 4180 divided by 305 gives me 13.7. Now, by now, you should have an inclination that 13.7 is so off the charts for degrees of freedom equal 19 that we know what we're going to conclude. You're going to end up rejecting the null hypothesis. Okay. If we want to know whether the tuition of the out of state is higher than the tuition of the in-state schools, the alternative hypothesis would be that mu sub d is greater than 0. If our test statistic were 13.5 and 19 degrees of freedom, let's see if I could find that value in my t-table. Again, 19 degrees of freedom, somewhere in there. But I'm noticing it's even to the further right of even that largest value, 3.883. So my upper tail area must be less than 0.0005, the p-value. So let's rephrase that. If the null hypothesis is true, if in fact there is no difference between in and out of state tuition, I should less than 5 out of every 10,000 experiments see a difference as large as the 4180 I did in fact see. My two choices here. Either I could reject the null hypothesis of equality because I saw something that was be unusual if there were, in fact, equality of the two means, the in-state and the out-of-state, or I would stick with the belief of the null hypothesis is true and just have to live with being extremely unlucky. I tend to think because my p-value is below alpha 0.05, I'm going to believe the alternative hypothesis. Okay, so let's move forward into something that really matters. In schizophrenia, we want to know if the size of the hippocampus is different in schizophrenics than non-schizophrenics. And the way you could do a lot of really solid medical research on these sorts of topics is via identical twins. There's a national twin registry for people who are identical twins. They can be part of it, and it's really helpful because if one of the two genetically identical humans ends up with a disease and the other one does not, you can say, well, it wasn't due to genetics, it must have been due to something else. And so you could look through the characteristics of these people's lives or physical conditions and see if there's a difference between them. In this case, the condition was schizophrenia. We have 15 brothers who were in their 50s who did not have schizophrenia, and their 15 twin pairs who did have schizophrenia. And I want to know how much of a difference there is between the affected and the unaffected brother in terms of their hippocampus volume. And this is in cubic centimeters. Okay, hippocampus being a brain part. I want to know how much larger or smaller, okay, is the hippocampus in the one with the disease than without, or if it was a hypothesis test question, is there a difference? So is the size of the hippocampus different? I would say a hypothesis test because I'm answering the question, is there a difference in the volume on average? Yes or no, hypothesis test. So let's go ahead and do that analysis. You could find all of what we've done via equation is sped up considerably if you were to do a use of the software. I'm just going to grab those two bits of information here, and I've got now output, and in my output it says, among other things, my p-value for the non-directional alternative hypothesis 0.006 for 14 degrees of freedom. In other words, I am pretty darn sure that there is a difference in the hippocampus volume between the brother with and the brother without the schizophrenia. If you want to sort of go with the differences themselves, the average of the differences is negative 0.19. The affected brother minus the unaffected brother is on average a negative 0.19, meaning the unaffected brother has a hippocampus volume that's about 0.2 higher. I could even get a confidence interval if I want. My standard error, overall, I get my test statistic T and an associated p-value. Here I would answer the question, is there a difference? Because my p-value is below 0.05, I'd say yes, there is. What about the confidence interval? Now that I say that there is a noticeable difference between the two groups, what is the size of that difference between the two groups? Confidence interval. My average difference is negative 0.2. My confidence interval is negative 0.07 to negative 0.33. In other words, the brother who is unaffected by schizophrenia has a hippocampus volume that's 0.03 to 0.33, I'm sorry, 0.07 to 0.33 larger than the brother with the disease. The larger the hippocampus volume, is going with the brother without the illness. So that either could be because the hippocampus size impacts the likelihood of developing schizophrenia. Smaller hippocampuses are more likely to have schizophrenia. Or it could be the other way around. Maybe the presence of schizophrenia is causing the hippocampus to be smaller. I can't tell which is cause and effect. I can simply say that between the two groups with these paired data, there's a noticeable difference, and that difference is such that whether a hypothesis test, we're saying there is a difference, or the confidence interval, we're telling you the size of that difference. And if I was a brain scientist, I could tell you whether a hippocampus volume of 0.06 is of practical significance or not. It's certainly statistically noticeable, however. Okay, so let's finish off some information that we've got, some problems that could come up. If you forget If you forget and use these data incorrectly, if you use the data incorrectly, you will have an errant conclusion. I'm going to tell you this. If I did not know that these two brothers were twin pairs, I would hit the wrong conclusion rather quickly. Okay, so let's change things up a little bit. I'm going to change the nature of the way the data table looks. And so that way you'll be able to try with the two sample hypothesis test, the independent sample hypothesis test, if you will. So I'm going to pause the recording to rearrange my data so you could see working it out. We would hit the wrong conclusion if we ignored the pairing information. So you can see now that if you have the data organized like this, where it's the volume in one column and then the disease status in another column, we could use the regular t-test procedure. So let's try that. Analyze fit y by x. Let's see if the volume is different between the two disease statuses. Yes and no for the hippocampus. So if I were to go ahead and turn on the t-test, I would have a conclusion of 0.06. I cannot spot a difference between the two groups. There's a lot of overlap in my two separate samples. Forgetting the pairing information will give us the wrong conclusion. My confidence interval is still centered at the right place, 0.09, but it's both negative and positive, the lower and the upper end. I cannot spot a difference between the two hippocampus volumes. So what's the point? The point is, if you have natural pairs of data, you got to use the paired method. The paired method is the right way to analyze the data if the data come in pairs. Okay, good place to stop for the moment, and we'll get back into it next video.